Welcome to Lesson 8 of Non-Euclidean Geometry. You may recall from a previous lesson we talked about parallel lines that had a common perpendicular. In this lesson we're going to talk about parallel lines that do not have a common perpendicular. In Lesson 5 we studied parallel lines that shared a common perpendicular. In this section we'll discuss the case of parallel lines that do not share a common perpendicular. We'll show later in this lesson that given a line L and a point P not on L, there are exactly two lines through P that are parallel to L but do not share a common perpendicular. Before we proceed, let's review a little bit from what we had done in Lesson 5. We had the case where we had a line L here and a point P not on L here. And from Theorem 13, we proved that there are an infinite number of lines through P that are parallel to L and that have a common perpendicular with L. In the figure below, the lines H, G, N pass through P and are parallel to L, and they have this common perpendicular AP with line L. Then there's also a line, or many lines, but just on this figure, there's one line here, M, that goes through P and intersects L. So in other words, not parallel to L. We have a couple theorems here that we're going to need in this lesson. They were first discussed in lesson number 5. We just talked about one of them, but let me read it again. Theorem 13, given any line L and a point P not on L, there exists an infinite many lines through P which are parallel to L and that have a common perpendicular with L. Then Theorem 14, let L be a line, P a point not on it, and A the perpendicular projection of P onto L, so similar to the picture we saw on the last slide. Among all the lines through P parallel to L and which have a common perpendicular with L, there is none that lies closest to AP, this common perpendicular, in the sense of making a smaller angle with it than do all the others. So this will come into play because the two lines that I mentioned that are parallel to L that don't share a common perpendicular are actually at the boundary of all these other lines that do share a common perpendicular. But we'll get to that. The main reason I've mentioned them here is so you don't have to page back to lesson 5. You can just take note of them here as we reference them in what follows. In the figure, we have a line L, a point P, and we drop a perpendicular down to L. It intersects at A, it makes a right angle here. Then we draw the line G that's perpendicular to AP. Under these conditions, there is a set of infinitely many lines that subdivide APD and that have a common perpendicular with L. This follows from the construction in the proof of Theorem 13. So I'm just showing one such line here, N. We can also go in the opposite direction and subdivide APC with an infinite number of lines that go through P that are parallel to L and have a common perpendicular with L. In each of these sets of infinite number of lines, there is no line that is closest to AP in the sense of making the smallest angle. So talking about this angle here. So here's our line N, and we can keep getting smaller and smaller angles in here and still have that line parallel to L and share a common perpendicular. There's no smallest angle. There's no line which makes the smallest angle. And the same thing on the other side here. Let's talk a little bit about the type of diagrams I'm using here. On the left, I have a diagram similar to what we had on the previous slide, a little bit different. Let's start with point P and the line L. As before, we're going to draw a perpendicular down from P to L. What's the intersection point at A? And as we noted, and as we proved earlier, there's an infinite number of lines through P that are parallel to L. And I've shown 3 here, H, G, and N. So they're all parallel. So the first point I want to make here in terms of the diagrams is that we're talking about hyperbolic space. So these, of course, don't look straight in Euclidean. I have them as being bent just to emphasize that this, for example, this line N here curves away from L and never actually intersects L. So that's just a drawing technique, but N, G, H, and L are all straight lines in hyperbolic geometry, as is M. However, M is not parallel to L. It intersects at point B. And what we'll show later in this lesson is that there's going to be a particular line, the first line in terms of this angle here between AP and the line, where the line intersects L. And then everything on the other side here, so N, G, and H are parallel. And then anything that has a steeper angle, for example, a line coming down this way, so anything steeper is going to intersect L, and anything on this side, for example, is not going to intersect L. So there's going to be a unique line, M, in each instance where you have a point P and a line L. There's going to be this kind of demarcation line. And then going on to the left, going in this direction here, there'll be yet another line that also demarcates between lines that intersect and lines that are parallel to line L. So that's one set of points I want to make. Now on the right, I have a model of hyperbolic geometry. There's multiple models and ways of drawing the lines and points. And one of them is called the Beltrami-Klein model. It's named after 2 mathematicians. And as I've noted here, points are represented by points inside of a unit disk, and lines are represented by chords. So if we took our diagram here minus the this line I added, we can represent it using this Beltrami-Klein model. So you see here the blue line is this chord H, and the black line is the chord N, and the green line here is the chord G. We have our points P and A just before, and this is our line L down here, and M is the line that intersects. So this is one of many ways of representing hyperbolic geometry. The reason I stopped here and to give a little bit of more background is the figures could easily confuse, and hopefully this explanation will help a little bit. Later on in a future lesson, I'll talk about several different models for representing hyperbolic geometry, but it turns out this technique I've used on the left is common in several textbooks, and it seems to be the easiest way to draw things. You just need to keep in mind where we're working in a curved space, and these things that look curved are actually straight lines in hyperbolic geometry. So let's take a similar figure that we've seen now in several slides. We have a line L and a point P, and we drop a perpendicular from P down to L and intersects at point A. We have a line G here that is a unique line that makes a 90-degree angle with AP. Let's now define the set S of all lines which subdivide A, P, D. So we're just working on the right side of the figure. We can make a completely analogous argument on the left side, but we won't need to do that. We'll just focus on the right side of the figure. So we take all those lines that subdivide APD, and we'll divide those into two sets here. The subdividers, which meet line L, so the lines that intersect L, and then the subdividers of APD that do not meet L. And we also have this terminology here that a line making a smaller acute angle with AP is said to precede the other line. So for example, H makes a smaller angle here, which where I'm pointing, with AP than N. So we would say that H precedes N. Now the claim I want to make here is every member of M, the lines that intersect L, precede N. And we can see that from our figure here. The way I've drawn it here now, we would have a contradiction, because if N and H actually preceded a line M that intersected L, they would make a smaller angle with AP, and therefore they would have to intersect L also. So these are drawn improperly, I guess you would say. They should be on the other side of the line M, and M should precede them, since M is intersecting the line L. Okay, so what we're going to eventually show, and I mentioned this in the previous slide, is there's going to be a unique line here, M, such that everything that makes a smaller angle with AP is going to intersect the line L, and everything that makes a bigger angle with AP is going to be parallel to L. But we haven't gotten there yet, but that's where we're going. So I'm just setting up some terminology here with precede and in these subdividers we just talked about. We have an intermediate result that holds both for Euclidean and hyperbolic geometry. We're going to need to use this in the next slide. If we have a angle here made by these two black lines, two rays, I guess they are, if the lines subdividing an angle are formed into two sets A and B, such that each line in A precedes each line in B, so we're talking about the lines coming out of the vertex here. So it's really a ray. Each ray in A precedes each ray in B. Then there's one or two things happen. Either A has a line preceded by every other line in A, so that's this dotted line here. So every other line in A would precede this line here, and this line is in A. Or B has this line, and it precedes every other line in B. So this precedes every other line in B. The particular subdivider is called the boundary between A and B. So the point is that you have an angle here, and you have all these subdividers, and you've broken them into two sets, where set A precedes B. Then this subdivider, this boundary, is either in A or it's in B. It's not in both. If it was in both, you'd have a contradiction in defining A to precede everything in A to precede everything in B. From the property that we stated on the previous slide, there exists the subdivider line B, which is the boundary between sets M and N. If you recall a couple slides back, M are the subdividers which meet line L, in other words, intersect line L, and N is the set of subdividers that do not meet line L. And our claim is the boundary subdivider B has got to be in this set N. It needs to be parallel to L. We'll prove that here. So again, here's our angle APD, and we're talking about subdividers of this angle here. So to prove this, assume the contrary, that B is in M. So in other words, B meets L at some point B, shown here in the figure. Next, select point C on line L, such that B is between A and C. So that's the case here as we've drawn it. By definition, the line PC is in M. right? It intersects the line L here and it goes through point P. And is preceded by B, since line B makes a smaller angle with AP than PC does. So we're talking about this angle here, AP and then line B. Then you see there's a bigger angle between AP and line PC. However, B being the boundary subdivider, it must be preceded by every other line in M, and so we have a contradiction, and therefore B must be in N. So this subdivider line must be parallel to L. So B is a line which does not meet L and goes through P and precedes all other lines in said N, and thus makes a smaller angle with AP than all other lines through point P that are parallel to L. But Theorem 14 told us that B cannot have a common perpendicular with L in that case, because there was no line that had there was no line that made the smallest angle with AP that had a common perpendicular with L. So we've found a line B which is goes through point P, is parallel to L, but does not have a common perpendicular with line L. And we could do the same thing on the left, which I'll mention on the next slide here. So again, this B was drawn in terms of a contradiction. In fact, it's parallel to L, so it's drawn incorrectly only because I was trying to prove this via contradiction. So B is a separator between the lines that are parallel and those that are not parallel to L that go through point P. A similar discussion as to that from the previous slide can be applied to the left side of the previous figures, and we would find that there's a line C which has a positive slope in this case, is parallel to L, goes through point P, but does not have a common perpendicular. What we'll show in the following slides is that all the lines between B and C, so anything going between these two lines, for example G, are parallel to L and do share a common perpendicular, and then only C and B go through point P, are parallel to L, but do not share a common perpendicular. And I'm showing also here these angles, alpha and beta, that B and C make with AP. And we'll also show later that alpha equals beta, as you might suspect given the symmetry of this argument and diagram. The following theorem summarizes some of our previous discussion. Given a line L and any point P not on it, so here's our line L, here's our point P, there exist exactly two lines, B and C, shown in the figure here, which go through P, are parallel to L, but do not have a common perpendicular with L. If A is the projection of P onto L, in other words, the parallel projection, perpendicular projection, then B and C make equal acute angles with AP. So these two angles are the same here. Within one pair of equal vertical angles, the angles marked as alpha in the figure, lies all the lines through P which meet L, and within the other pair of vertical angles, these theta, lie all the parallels to L through P which have a common perpendicular. So let's just summarize this here. We have a line and a point, and we have these two lines C and B that are parallel, but they don't share a common perpendicular with L. And then all the lines that go between C and B, so everything that goes in between here, for example G, is parallel to L and does have a common perpendicular. And then all the lines that make a smaller angle with AP. In other words, all the lines that go through here and here within angle alpha intersect the line L. We also have some terminology. The lines B and C in the figure will be referred to as boundary parallels to L through point P. The other parallels to L through P are called non-boundary parallels, for example, G. So all the lines going through P and between C and B, they're called non-boundary parallels. The equal angles, alpha here and here, are called the angles of parallelism corresponding to line L through point P and point P. The sides of the angles which lie on a B and C are called the boundary rays. So we're talking about here and here. They're the boundary rays. So basically half of line C and half of line B, just what's pointing out this way. In the figure, PF and PE are the boundary rays. So going out this way and that way, as I just mentioned. Okay, so we have some terminology and a summary of our results thus far. Theorem 32 follows pretty directly from our Theorem 31 on the previous slide. Consider the boundary parallels B and C to line L through point P. If Q is any point on L and R is any point on a boundary ray, then every line subdividing QPR intersects L. And I have an example of what's stated in the theorem here. So we have P, point P, and the line L, and then B and C are the boundary parallels to L. And we know that every line going through here is parallel to L and has a common perpendicular, and every line going between B and C, between here and here, intersects the line L. And so a bisector of QPR, for example, this dotted line, clearly would intersect L because it's between these B and C here. The following theorem provides a condition for when a line is a boundary parallel to another line. If two non-intersecting lines, M and L, are intersected by a transversal N in points P and Q, respectively, and every line subdividing one of the interior angles at P intersects L, then M is a boundary parallel to L going through P. So we have an example here of what's being stated. We have lines M and L and this transversal N that intersects the two lines at P and Q. And the theorem says if every line subdividing one of the interior angles, so say here, of at P intersects L, then M is a boundary parallel to L going through the point P. In the figure, we have a line L and 3 points P, Q, and R, and then for each point we've dropped a perpendicular down from the point to the line. See here. And we also have these parallels to the line L. So C, B, D, E, F, and G are all parallel to L. We could talk about two different directions of parallelism. B, E, and G all point to the right in the sense of making an acute angle with the associated perpendicular on the right, and then again here on the right. And then C, D, and F all point to the left. And in general, we can talk about directions of parallelism. There's always two. We could, for example, rotate this entire figure 90 degrees, and then we would be talking about parallels going up and parallels going down. The point is there's only two possible directions. and these are known as directions of parallelism. Given theorem 35 from the previous slide, we can speak of two boundary parallels relative to each other in lieu of saying two boundary parallels to a given line. So with that in mind, we can state the following theorem. If two boundary parallels relative to each other are intersected by a transversal, and alpha and beta are the interior angles such that one side of each is a boundary ray, then alpha plus beta is less than 180 degrees. So we have a picture here of what's being stated. We have M and N, and they're boundary parallels to each other. And then we have these interior angles, alpha and beta. And the theorem is claiming that the sum of these two is less than 180 degrees. We have a few cases. We'll do the first one here on this slide and then the other cases on the next slide. So if L is perpendicular to one of the parallels, M or N, this line L, so for example, if beta is 90 degrees, then one of the interior angles is 90 degrees, and the other angle of parallelism, which would be acute by theorem 31, and thus the sum of the two would be less than 180. So that's the first case where we just have one of these two being 90 degrees. Let's look at the other cases on the next slide. Okay, next we suppose the transversal L is not perpendicular to M or N. We have three cases under this condition. First, alpha plus beta equals 180 degrees. And we also know that beta plus gamma is 180 because this N is a straight line. Thus, alternate interior angles, alpha and gamma, are equal. And the lines M and N have a common perpendicular by theorem 10, which I've copied down here so you don't need the page back to less than 5 where this comes from. And that contradicts the assumption that M and N are boundary parallels. So this case is out. Then we have a similar problem here. If alpha plus beta is greater than 180 degrees, then we can subdivide alpha with some line K, making an angle delta such that delta plus beta is 180 degrees. And in that case, gamma is equal to delta, and thus N and K are parallel lines with a common perpendicular by theorem 10 again. However, this is impossible since K is a subdivider of A and must intersect N by theorem 31. So that's another contradiction. And so we've excluded everything except for the case where alpha plus beta is less than 180 degrees, which is what we wanted to prove. So that is the last slide in this lesson. I have still several more. Things get a bit more complex as we build up our theory, but I'll try to go through it as thoroughly as I can and get you up to date on non-Euclidean hyperbolic geometry.